Welcome to our lesson on solving matrix equations in the form AX equals B. In this video, we'll learn how to find general solutions to matrix equations and describe their solution sets. Let's start by understanding what this equation means and the general approach to solving it. A is an m by n matrix, X is an n-dimensional vector of unknowns, and B is an m-dimensional vector. Our goal is to find all values of X that satisfy this equation. Here's our step-by-step approach to solving matrix equations. Step 1, write the augmented matrix. Step 2, row reduce to reduced row echelon form, RREF. Step 3, determine whether the system is consistent. Step 4, find one particular solution. Step 5, find the homogeneous solution space. Step 6, combine to form the general solution. Let's look at each step in more detail. Step 1, we form the augmented matrix by placing matrix A and vector B side by side. For example, if we have A and B like this, the augmented matrix would look like this. Step 2, we row reduce the augmented matrix to reduced row echelon form, RREF. We use elementary row operations, swapping rows, multiplying a row by a non-zero scalar, and adding a multiple of one row to another row. The goal is to get the matrix into RREF, where the leading entry in each non-zero row is 1. Each leading 1 is to the right of the leading 1 in the row above it. Each column containing a leading 1 has zeros elsewhere. All rows of all zeros are at the bottom. Let's see how row reduction works with our example. We start with the augmented matrix. First, we subtract 3 times row 1 from row 2. Next, we multiply row 2 by -1/2. Finally, we subtract 2 times row 2 from row 1. The result is the RREF of our augmented matrix. Step 3. Determine whether the system is consistent. A system is consistent if it has at least one solution. It's inconsistent if it has no solutions. We can tell by looking at the RREF. If there's a row with all zeros to the left of the vertical line, but a non-zero entry to the right, the system is inconsistent. In our example, there are no such rows, so the system is consistent. Step 4, find one particular solution. From the RREF, we can read off a particular solution. Columns with leading ones correspond to pivot variables. Columns without leading ones correspond to free variables. We set the free variables to 0 and solve for the pivot variables. In our example, both variables are pivot variables. Reading from the RREF, we get x equals 1 and x2 equals 2. Step 5, find the homogeneous solution space. The homogeneous equation, AX equals 0, corresponds to the matrix equation, where B equals the 0 vector. The set of all solutions to this homogeneous equation is called the null space of A. We can find a basis for the null space by row reducing the matrix A and finding the general solution to AX equals 0. Each free variable corresponds to a basis vector in the null space. In our example, there are no free variables, so the null space contains only the 0 vector. Step 6, combine to form the general solution. The general solution to AX equals B is the sum of a particular solution plus any vector in the null space of A. Mathematically, X equals X particular plus X homogeneous. If we have k free variables, the general solution can be written as x equals x particular plus t times v plus t2 times v2, and so on up to t underscore k times v underscore k, where the v's form a basis for the null space and the t's are parameters. In our example, the general solution is just the particular solution. X equals the vector with components 1 and 2. Now let's look at an example with infinitely many solutions. Solve the matrix equation where A equals the matrix with rows 1, 2, -1 and 2 for -2, and B equals the vector with components 3 and 6. We start by forming the augmented matrix. After row reduction, we get the RREF. We have one pivot in column 1, and columns 2 and 3 contain free variables. Let's set x2 equals s and x3 equals t, where s and t are parameters. From row 1, we get x equals 3 minus 2s plus t. A particular solution is x equals 3, x2 equals 0, x3 equals 0, which we get by setting s equals t equals 0. The null space is spanned by the vectors -2, 1, 0, and 1, 0, 1. The general solution is the vector with components 3, 0, 0 plus s times the vector with components -2, 1, 0 plus t times the vector with components 1, 0, 1, where s and t are any real numbers. Let's understand the geometric interpretation of the solution set. When there are no free variables, the solution is a unique point in space. When there is one free variable, the solution set is a line in space. When there are two free variables, the solution set is a plane in space. And with more free variables, the solution set is a higher dimensional hyperplane. In our second example, the solution set is a plane in 3D space, passing through the point with coordinates 3, 0, 0. In summary, to solve the matrix equation, AX equals B, first, row reduce the augmented matrix, AB, to RREF. Check for consistency by looking for 0 rows with non-zero right-hand sides. Identify pivot and free variables. Find a particular solution by setting free variables to 0. Find the null space of A by solving AX equals 0. The general solution is the particular solution plus any vector in the null space. Remember the 3 possible outcomes: unique solution, no free variables; infinitely many solutions, at least one free variable; no solution, inconsistent system. Thank you for watching.